Here are the notes for section 6.1, day 54, and also day 54 includes the first part of section 6.2. So this is our second day on section 6.1. The title is Slope Fields and Euler's Method, and Euler's Method looks like this. If you have a function, you can create a linear approximation that jumps from point to point using the point, the slope, and then a change in y. So the process is start at a point, calculate the slope of the tangent line at that point, and then calculate a new y, a delta y, by rearranging the definition of slope. Slope is change in y over change in x. If we move the delta x to the right side, the change in y is slope times delta x. Now, as we move from point to point, they will tell you what delta x should be. So in this situation, the differential equation is y prime equals y squared plus 1. That's the slope. Our initial point, or our starting point, is x is 1, y is 0. So that's the starting point there. In two steps, we're going to have a delta x or an h of 1/2. H and delta x are the same thing. So here's what you do. Take this point, plug it into your slope. Slope is y squared plus 1, so I take the y value squared, add 1, and I get 1. The slope of the tangent line at this point is 1. So if I use a step size of 1/2, slope times delta x of 1/2 is 1/2. I'm going to take that delta y 1/2 and add it onto the old y and get a new y of 1/2. Delta x is 1/2, like we defined earlier. H and delta x are the same thing, so I take 1, add a half, and now I'm at this point, 1 and 1/2, 1/2. So starting at A, I used a linear approximation to move to the point 1.5 and 0.5, and you can see that that approximation is pretty close to the solution line. This differential equation gives slopes. It does not give the equation of this line. So the next thing to do is to take this point, again, plug it into the slope formula. We're finding a new tangent line slope. So y squared plus 1 is 5/4. I'm going to use that to calculate a delta y. Delta y is the slope of 5/4 times the delta x, which is 1/2, and I get 5/8. So I'm going to increase my y value by 5/8. So if I started at a half, which is 4/8, and if I add 5/8, I get 9/8. When I increase my x again by 1/2, I'm at 2 9/8. So 2 9/8. And now we see that the approximation point is starting to be very much different than the actual point. So linear approximations work in small neighborhoods or in small steps, but after a while the linear approximations start to deviate from the true relationship. So the end of the Euler's process gives us this point. We didn't really solve the differential equation, but we approximated points along that differential equation. And as practice, we can actually find the equation that solves this differential equation. So we want to solve this for y. So again, y prime is y squared plus 1. Y prime is dy dx. Separation of variables, move the dx to the right side. Move all of this, the y squared and the plus 1, to the left side. You can't subtract. That's not going to do you any good. Dy minus y squared. So you're going to divide by the entire right side and get dy over y squared plus 1. Take the antiderivative. This is what we just learned in a previous section. The antiderivative of dy over y squared plus 1 is the inverse tangent of y. X plus a constant. We started at the point 1, 0. So if I plug 1 in for x and 0 in for y, I get this statement. The inverse tangent of 0 is 0. So c is -1. Plugging that back in. Inverse tangent of y equals x minus 1. Solving for y, we get y equals the tangent of x minus 1. If you remember what a tangent graph looks like, we're taking a tangent graph and moving it right 1 unit. So this blue line does seem to make sense as a solution to this differential equation. This is a second example of Euler's method, but the numbers get really ugly very quickly, so we're not going to finish all of it. Different differential equation, y prime equals y squared. We're starting at the point 0, 1/2, 0, 1/2, so we're starting there. We want to go 5 steps, and we want each step, or delta x, to be 0.2. So set up your first point. Use this point in your slope formula. The slope is y squared, so I'm going to take 1/2 squared and get 1/4. Delta y is slope times delta x. 1/4 times 0.2 is 0.05. That's my delta y. So I'm going to take 0.5, add on 0.05, and get 0.55. X increased by 0.2 each time. H is the same thing as delta x. So I'm now sitting at the point 0.2, 0.55. 0.2, 0.55. And again, this point is a really good approximation for a point along the solution curve. Repeating, take the y value and square it to get a new slope. Take the slope, plug it into m times delta x. 0.3025 times 0.2 is 0.0605. That's our delta y. Add that on to 0.55. Your delta x is still 0.2, so I'm now at the point of 0.4 for x, 0.6105 for y, 0.4 for x, 0.6105 for y. Again, pretty close to the actual solution curve. I can use this point in the slope formula. 0.0605 squared is this quantity. This times 0.2 is my new delta y, etc., etc. So when the decimals start to get this ugly, I'm going to give up on this problem. But you can see by plotting these points that for this situation, the Euler's method, which moves from point to point using linear approximations, hugs the real solution pretty closely. So as more practice for solving differential equations, the solution to this differential equation is this curve here. Take and solve this. Pause the video, set up dy dx equals y squared, and see if you can solve it. And don't forget about the initial condition 0, 1/2. You're starting with a y-intercept of 1/2. Okay, moving the elephant out of the way to reveal the solution. dy dx is y squared. When you bring the y squared to the other side, it's dy over y squared, which is the same thing as y to the negative 2 times dy. And then dx on the right side. Taking the antiderivatives, you get negative y to the negative 1 equals x plus c. The initial condition, x is 0, y is 1/2, 0. The reciprocal of 1/2 is 2, and there's still a negative sign there, so you get 2 equals c, negative 2 equals c. Plugging that back in, we still have 1 over y here, so if you bring the y to the right side by multiplication and divide by x minus 2, bring the negative over as well, you have y equals negative 1 over x minus 2. So this is the rational function 1 over x that's been moved right to and flipped across the y-axis. So the y-intercept of 1/2 makes sense. Plug in 0 for x, you get 1/2 for y. And if you take the reciprocal function, move it right to, and then flip it, you should have the point 1, 1, which indeed we do. So this is the solution curve, and Euler's method, had we carried it all the way through, is a very good linear approximation to that differential equation. So the last slide for this day 54 derives a famous formula that you've seen in your pre-calc class and then applies it to a financial situation. So this says the growth rate of a population is proportional to the population size. Growth rate is a differential, dy dt, means equals proportional to the population size. So k is a proportionality constant and the population size is y. What this means is that as your y value gets bigger, your growth rate also increases. So separation of variables, bring the dt to the right side, bring just the y to the left side. So we have dy over y is k dt. Take the antiderivative of both sides. Natural log of y is kt plus a constant. The t shows up because you have dt here, not dx, but dt. Exponentiating both sides, e to the natural log of y is y. E to the right side produces this. You can say that e to the kt plus c is the same thing as e to the c times e to the kt. A lot of people replace this e to the c with a big capital C. So now we have y equals capital C e to the kt. With the initial condition of 0 and y0, plug in 0 for time, plug in y0 for y. E to the 0 is 1, so you've got capital C is y0. So the final solution is the amount that you have is the initial amount times e raised to the kt, or exponential growth. In pre-calc, you saw this as the number of items is the original number of items times this exponential growth factor e to the kt. So you've derived the exponential growth formula. So applying this to this example, my tax refund dissipates at a rate proportional to the amount remaining. If 20% is spent after 3 months, when will 95% be spent? So this 20% after 3 months is like an initial condition. First thing we need to do is take n equals NO e to the kt and put it in terms of this refund. So the amount remaining of my refund is whatever my refund started at, the initial refund amount, times e to the kt. And I have two constants that I need to find, the initial amount and this k here. So I've defined my growth equation, I've defined my variables, and the trick here is if 20% is spent, that means that 80% is remaining. So this R, the amount that I have, is replaced by 0.8 RO. I don't know how much I had initially, but I know that after 3 months, I have 80% of that initial amount. Well, the ROs cancel. To get the 3 to the other side, I take both sides and raise it to the 1/3 power, so e to the k is 0.8 to the 1/3. Whatever number that is, I'm storing that in A, and I'm actually not going to solve for k, I'm just going to leave it as e to the k. And the reason for that is that this 0.928 has an interpretation value. Because this is less than 1, that means that I have decay. My initial amount times a number less than 1 means I'm going to have less than my initial amount. In other words, I'm spending my refund. As time goes on, this number is going to keep getting multiplied by itself, which means RO is going to be multiplied by a smaller and smaller amount. So continuing on, 95% spent means that 5% remains. So again, I'm going to take my remaining variable and call it 0.05 of the initial, 0.05 RO. Right side is this growth term, 0.928 raised to the t. This A circled means that I stored this number in a memory value, in the memory of A on my calculator. You do not want to round this. If you round in exponential functions, you could be way off. So whatever number you get here, immediately store that in A. Dividing both sides by RO makes that disappear. Logging both sides lets the exponent t come out front, and then t is just the natural log of 0.05 divided by the natural log of that number that I stored in A, and I get roughly 40.3 months, which seems like a reasonable statement. And that's it for day 54.